One thing to remember before I even start off is that at its heart, clamp-on ultrasonic is a non-intrusive flow measurement system. So in short, clamp-on ultrasonic goes on the outside of the pipe, non-intrusive. You can install it while you're still flowing. You don't have to open the pipe, cut the pipe, stop the flow upstream or downstream or any of that. So that's great. How does this whole thing work? There we go. So our clamp-on ultrasonic is part of a much larger process instrumentation offering that Siemens offers that FLW supplies to their regions. We do flow, of which clamp is part of. We measure level with both ultrasonic and radar, as well as guided wave radar. We do valve positioners. We measure temperature. We do pressure. We do dynamic weighing for solids, such as weigh feeders and scales and mass balances, and load cells, and of course offering a slew of services that FLW helps us supply to our customers. So our process instrumentation, the flow stuff, is just part of what we do. Now, the clamp on ultrasonic basically refers to field installed meters. So these are, as I mentioned, externally mounted transducers. A transducer both sends and listens for transmission signals, and these signals come from the transducers, and we'll talk a lot more about that in a minute. But they're designed specifically for external mounting in the worst conditions, underwater, out in the desert, in the backyard, by the chemical plant, to be mounted on plastic pipes, to be mounted on metal pipes, whatever kind of pipes you have, uh, even lined pipes, not a problem. They offer an accuracy from 0.5% to 1% of rate or better. Now, when they're talking about ultrasonic, sometimes it's important to get a fundamental understanding when they're talking, what does that mean? Well, ultrasound or ultrasonic just means sound beyond the range of human hearing. So typically the average baseline setting for human hearing is 20 to 20,000 hertz. Okay. So ultrasound would be above that. So it's ultrasound is beyond the realm of human hearing, but it's very much exactly like a bell ringing, but it's ringing outside of the range of our ability to hear it. Now, when you're looking at a clamp-on ultrasonic system, the fundamental components look like this. You have a transmitter, which is really the flow computer, and what its job is to send signals to transducers that are set on a pipe, and then the transducers ring like a bell, and then ring the pipe, and the pipe gets a signal injected into it, bounces off the wall of the pipe, and then back to the other transducer that the flow computer actually listens for. So these transducers both send and receive, and the signal just goes back and forth. And that's great. And what does these things really look like when you're not talking about a cartoon diagram? These are real actual components. The transducers, as you can see, can be quite small for small thin-walled pipes, and can be quite large for the larger, thicker walled pipes. And the reason for that is that just like a bell, you would not have a very small clangor on a very large bell. You would need a larger gong or clangor on them in order for them to work appropriately. So that's what these are for. So the bigger the thicker the pipe, the larger the transducer that's needed. One thing I did want to mention here before I went on is that there's also an availability of an RTD or temperature input. And there's actually a couple of temperature inputs depending on how accurate you want to be. For example, if you're measuring natural gas, it's important to get not only the temperature for the correction factor for the gas, if you're correcting to a specific temperature, but also because the pipe gets bigger, the hotter it gets. So the RTD input helps correct for both those changes in temperature. Now, a typical field installation looks something like this. This is a dual beam where you have two sets of transducers on a pipe. This is a very popular natural gas or oil or petroleum type application. And then the signals are all run in the conduit, either flexible or hard pipe, and then they're run over to the transmitter over here. So basically, that's all that's required. No drilling, just some straps on the pipe. Sometimes you can just use magnets if it's a temporary install. Very easy, very quick, and very accurate without any disruption on the flow. So now that I've gone on and talked about how great this thing is, let me talk a little bit about how it works. It works on the principle of transit time. Now, if you can imagine this graphic of a stream was a pipeline, and the canoers on the pipeline, the canoers that are going downstream with the current will arrive much faster than the poor guys that have to canoe upstream, just like that. So the time difference between the people going upstream and the people going downstream is directly related to the speed of the flow in the stream or the river. So that transit time between those 2 points can tell us how fast the current is. Now, in a piece of pipe, such as this, these are transducers. One will shoot into the pipe, reflect off, bounce off the bottom, and up into the top, the other transducer. And then that transducer will then inject a signal into the pipe stream, bounce off, and be recorded there. Now, if there's a no flow condition, the upstream and the downstream flow will be at exactly the same pace, at exactly the same time. So the time downstream will be the same as the time upstream. But as soon as there's a current, or in this case, a flow, the flow rate can be determined by the time difference of the reflection of the upstream versus downstream flow. It's really that simple. So it's all a matter of how fast the time it takes to go against the current. I would also like to mention that if there are questions, I know you can definitely mention them in the chat, and I invite you to do so during the presentation. Don't wait. So how does it all work? Well, in the transducer, there is a piezo stack. The piezo stack is hit with electricity and it oscillates. That frequency then is transmitted directly to the pipe through either an acoustic mat or an acoustic gel. Okay, hold on. That was a good question. All right. So the temperature limit on the high end is 446 degrees F on the high end. On the low end, I believe it is -50. I'll have to double check that. What was the question is what are the temperature limitations and how does the insulation affect, so, and is that, and it's either insulation or installation, I'm not sure, affect these measurements? Well, to be short and sweet about it is that if you're putting them up on an Alaska pipeline, which we have meters that have actively been working for many years, they're mounted and they're installed with a little bit of insulation. The pipes are usually warm, and that doesn't usually promote any problems, especially if the pipes are flowing. If it's extremely hot, we have these working at 120, 130 degrees Fahrenheit out in the deserts in Dubai. None of that has been a problem either. So it doesn't affect the installation whatsoever because it's a physical installation. It's strapped to the pipe. But you have to be aware that if you're going to cause frost or anything like that, you want to make sure that that's protected. It usually isn't a problem. It's just like if you're putting it underwater, you actually have to waterproof it. All right. Thanks, Sean. That was a good question. All right, back to where we were. So, how does it work? I talked about the piezo effect, which is just putting a little electricity on a set of piezo crystals. And as you can see, what they do is they just oscillate and they ring the pipe through an acoustic stratum. So either an acoustic mat or acoustic gel. The acoustic gel is installed about once every 2 or 3 years, depending on the environment. The acoustic mats are a permanent install. So as I stated earlier, the transducers these guys are both senders and receivers. So they send the signal, they receive the signal, and they transmit that information back to the flow transmitter. So to kind of put a final ring on the end of why we have all these transducer different sizes is each pipe has a different type of sound. A thin wall tube will have a high frequency. Intermediate sized tube will be an intermediate frequency, and the thicker tubes will have a very low or deep sound. So each one of these types of pipes, each one of these types of materials, and each one of these types of flow mediums can affect the harmonics of the flow. For that reason, that there are a dizzying array of, uh, of transducer options. Now, I skipped over a lot of interesting stuff because, in the interest of time, because everybody's got lunch and it's only an hour. But basically, when we talk about a clamp on ultrasonic from Siemens, typically what we're talking about in some of our higher end, more critical applications is direct reflect mode. Now, that direct reflect mode is that actual bouncing it off one side of the pipe that we talked about earlier. And the reason we like that is because the direct reflect mode provides an extremely broad footprint of signal, a lot of signal into the pipe, bouncing off and then back up. So you have two paths of information down and then back up for each send in this case. Now that can be altered. There's a lot of other stuff that I'm leaving out, but the fundamental part is that if there are particulate matters or air bubbles in this type of installation, you have the opportunity to be able to overcome the noise or the interference that the particulates or the gas bubbles can create. Because you can imagine if there was a piece of rust or something, this signal would bounce back immediately. But with a very broad footprint on a direct reflect mode on a pipe, this gets you a chance to have a lot of information and overcome a lot of noise resistance. So you can have 10% particulate or air bubbles disrupting the sound here, but in a direct shot on a wetted set of transducers, one air bubble can shut you down. That was the message here. So we use a very wide footprint and we use a direct reflect. Now I've gone ahead and said that, I would like to mention that it is possible under some situations, under extremely challenging conditions, where we can mount these transducers clamp-on style in a direct mode. The reason you would do that is that if you had an extremely challenging flow with a lot of turbulence or a lot of interruptions, and you just had to shoot direct, you can do that. We would prefer to do it the other way because we can get a lot more information and be a lot more accurate over a wider range of conditions, but you can mount direct if so required. All right. Okay, so I mentioned very at the beginning there about, well, you can have a single path or you can have a dual path. Well, you can also have a 4-path or a 3-path. And the reason that we do that is because, as I just stated earlier, whereas the reflect puts us in the pipe for an awful long time, doubling the amount of paths covers a lot more of the pipe. And that's good for not just particulate matter or air bubbles, but turbulence. So if you had a slight bend in the pipe, if there was a disruption because of a valve was left half open, or if whatever, you had a reducer or an expander somewhere around, and the flow profile wasn't just perfect, having all of this extra coverage with just dual beams, doubling the amount of information you can pull off the pipe, can help correct for an awful lot of flow variations. 4 paths puts almost 80% of the flow in that pipe under examination. So that's for super accurate or super challenging flow applications. And it's interesting to note that on a clamp-on ultrasonic meter, if you were to lose a channel or just a transducer, the meter continues to work with just about the same accuracy. We've had animals break these off. We've had, um, you know, vehicles knock them off, and you just lose a path. but the other paths take over and they just average it out. But again, the reason for the multi-path is just to get more information out of the pipe. Okay, so somebody just asked the question, um, the flow meter upstream pipeline configuration is changing based on valve operation, and we can see an effect currently in dual paths. Can we upgrade to 4? Okay, so if you currently have a dual path system, you'd actually have to change the transmitter in order and buy an additional 2 sets of sensors and mounts. The transmitters are set up to be, when you buy them, either single path, dual path, or 4-path. So if you currently have a dual path system, it would be just a matter of getting an additional transmitter and the additional hardware to create the extra paths. So if you have a single path or a dual path system, you can upgrade it, but you'd have to change the transmitter to do so. Good question. So flow profile, yeah, kind of filling right into what we were discussing just a slide ago. Well, what happens if you don't have just the right flow profile, where you have elbows out of plane or double 90 degrees, or you could have all kinds of flow effects that would delaminarize the flow, which will change the velocity in different parts of the pipe. So if the velocity is 10 feet per second here, it's 12 feet per second around the inside of a bend, then the problem is that where are you measuring it? So the solution for that is we call it a disturbed flow profile adjustment. There's a number of different names for it. But basically what it does is it allows the user to install the transducers where they have the room. And if you have some bends and if you have an expander or a reducer, you can tell the transmitter, hey, this is the setup I have. I don't have the proper, you know, 10 or 5, a 10 before and 5 after, or 20 before or 5 or 10 after. You can tell the transmitter I have a disturbed flow condition. And what the meter does internally is correct for that and will actually help digitally laminize the flow, calculate that with an algorithm. It's built into all the transmitters, by the way. And this is this is actually how you go and protect it. So it's the stirred flow profile. You tell it what's your upstream distance, what do you actually have in your line, is single elbow, double elbow, etc., in plane or out of plane. And the meter will correct for that. So we prefer to have the installation done the way the book says, but the reality of the world is that rarely gets to happen. And this system is built for real world applications. So the disturbed flow profile system allows you to install it where you need it, not where the meter wants to be. So some of the hardware, as far as overall pictures and stuff, this is our FS220. This is a liquid flow meter only. It's primarily for the water and wastewater industry. It's a relatively cost-effective installation. It is not pricey at all. It's a single channel system, and we usually use these, as I said, in a water and wastewater. We use it as a check meter in some chemical applications where they don't need approvals. But if you need approvals, you move over to the 030. So the 030 is the workhorse of the line. This measures not only liquid flows, but also gaseous flows. So natural gas, hydrogen, oxygen, excuse me, whatever, what have you. And the 020 is a single channel, single path, whereas the 030 can go up to 4 paths. So some of the cool things about this is the pricing, is that once the pipe gets sufficiently large, say 15, 16, 18, 20, 24 inches and bigger, um, these become extremely affordable because you're only buying the transmitter and the transducers and the cables. You're not buying a huge hunk of metal. It all comes. So if you bought a 20-inch pipe system and then bought a 300-inch system or a 300-inch, 350-inch system, it's the same pieces of electronics. It all looks the same. So the cost does not go up when the pipe size goes up. So Any of these systems in liquid flow can handle pipes from half an inch up to about 33 feet in diameter. So huge penstock types of pipes. The turndown ratio is about 400 to 1. The system offers zero pressure drop. Flow can go backwards or forwards, and the totalizer can be set up to do flow all in one direction, flow in both directions, or a net flow type of setup. If you want to put these into an existing system, for example, you may have a mag flow meter in line, but you want to have an ability to double check the magnetic flow meter. You can put one of these right next to the magnetic flow meter and have a check system. So just in case the mag meter goes down, you're still measuring flow and still correcting flow. All right, good question. Okay, I'm going to take a pause. Rod asks, what's the maximum allowed length of cable? Awesome, you're playing into my hand here. So there are two types of cables. There are the cables that we've been seeing here, which are the standard coax, and they could be quite long, depending on the type of meter. If it's an approved area, the maximum length is about 60 feet. But wait, there's more. Hold on. On an unapproved meter, they could be about 300 feet or more. But if you have the requirement to mount your transducers in an application that is hundreds and hundreds of feet away from the transmitter, it happens sometimes. The system that we have available allows us to mount the transducers and the bulk of the electronics right next to the pipe in a Class 1 Division 1 approved area, and then run a digital cable hundreds, 300, 400, 500 feet away directly into the transmitter. And that's called a DSL, or a digital sensor link. There is a built-in DSL in every single one of these units, but if we pull the DSL out and mount it on a standpipe, these transducers can have a cable 65 feet or 5 feet. And then you can go 300, 400 feet away into the transmitter with the SSL cable, or the digital signal cable. So that kind of adds to the benefits because these cables are costly. So if you had a 4-path system in a Class 1 Division 1 area, then you could be spending thousands and thousands of dollars on cables that are just 10 meters long, or 30 feet. But with the SSL cable, it's pennies a foot. So you choose short cables at the install site and then run the digital cable out to the transmitter. And the added benefit to the cost is signal degradation. It's a digital signal on a Modbus line, and instead of an analog signal running through high resistance coax cable, you're running on an SSL cable. So if you have external noise, you have a VFD or a pump or something, the digital signal is not disrupted or affected by that. So that is an awesome question. All right, hang on. We've got more questions coming in. All right, I love these. Okay, so for gas applications, how do you compensate for temperature or pressure? Well, we compensate with temperature with an RTD. Okay, so there's an RTD that, if it's a gas flow, there's an RTD that mounts, it's a clamp-on RTD instead of a thermal well that mounts on the outside of the pipe and monitors the temperature of the pipe. And that allows us to correct for temperature variations within the pipe. For pressure, what's interesting is that because we know what's in the pipe, and we know what's in the pipe because of the speed of sound of the signal. So the speed of sound in the transmit and receive mode tells us the speed of sound in the fluid, be it a gaseous fluid or a liquid fluid. And because of that, we can identify what the material is. Because we know what it is, even if it's natural gas with the slight variations, we can apply changes in speed of sound to changes in pressure, which changes the density of the material. So that's some of the ways we compensate for both temperature and pressure variations. The next question is, will they work submerged? And they emphatically do work submerged. Transducers work submerged. I wouldn't want to submerge a transmitter. They're only good for 3 feet, 1 meter of submersion. The transmitters, so I wouldn't want to leave them permanently underwater, but the transducers can be permanently mounted, submerged for eternity in water. All right. What have I missed? Okay. All right. So talking a little bit about the 220, I think I've hit most of the high points. They are extremely easy to set up and use. It's a single channel unit. All the information you need to set it up, you can actually derive from the device. So if it hasn't been, sized to the where you put the transducers, how you mount it on a pipe, all that information comes from the transmitter. The 220 offers a 1% or better accuracy. A lot of that depends on how you mount it. If you do a great job mounting it with a proper run length, then you're fine. If are not compensating for a bend, you haven't gone into the disturbed flow, the accuracy can degrade. But there are ways to always improve that by modifying the installation. All right. There's also, I don't want to skip this, there's also a built-in micro SD card that holds up to 64 gigs of memory. Now that also holds a lot of the calibration and the setup data, but you can also write to the micro SD card for performance. So what is the speed of sound? How's that changed? What is the flow rate? What has that been? What are the totalized values? And you can send that to the micro SD card, and you can hold that data there and pull it out and stick it into a computer and have a full record of the performance of that meter. Okay. So the 290 is a portable battery operated version of the 220. So the 290 is a NEMA 4X IP65 enclosure that protects the device to be used outside. It runs on a battery or AC powered, so you can just plug it into the wall, or the battery will power it for 24 hours or more, at least 24 hours, but usually more. The batteries take about 2 hours to charge, and once charged, batteries can be hot swapped. So if you're measuring flow and you don't want to disturb the flow, but you got to change the battery and you don't have an AC outlet, it's easy enough to just change batteries. You've got about 4 or 5 minutes to change them while in operation without losing power. So they can be easily hot swapped. They also have the same flash memory that we were talking about, up to 64 gigs. The Siemens hardware, which comes with it, which is quite interesting, it can be permanently mounted, just like a regular set of transducers, but there are magnetic mounts with rare earth magnet mounts that you can just stick on there for a temporary mount to do a flow check or to do a flow verification or validation on another piece. Or if you want to see if there's any velocity, if you have a valve that's closed, you put the transducer on, you can evaluate what the speed is and whether or not there's any difference upstream and downstream, and you can tell whether or not the valve is leaking. A lot of people use it for that. So it's a check meter, it's a flow meter. You can use it as a permanent install, but it's really designed to be moved around. It stores up to 20 locations within its memory. So you can actually take this and program it. And then when you want to go back to that site, you just recall the site, and installation takes 5 minutes instead of 40 minutes or less. As I stated earlier, you can use high temperature transducers, good to 446 degrees, and again, IP67 installation. The 230, which is our workhorse, is a liquid system or a gas system. It can utilize an internal or external digital sensor link. This is a picture of the external digital sensor link that we were talking about that allows you to wire a device and then take it hundreds of feet away with a digital signal directly into the device. This is a class 1 division 1 enclosure, so you can pretty much put it anywhere where you're going to want to flow. The standard 230 comes with a DSL built in, and the digital sensor link is just what takes the information in, converts it into a digital signal so that the internal processors can use it. See, 4-pass we talked about, IP66. It is FM approved. It also has ATEX if anybody cares. In the United States, not many do. The standard transmitter itself is a Class 1 Division 2 install. The external DSL is Class 1 Division 1, and the transducers are Class 1 Division 1. The transmitter can be powered via 24 volts or 240 or 100 to 110, 120, whatever you happen to have. And it's self-switching. It's a universal power supply, so you don't have to change just because your power has changed. The question was, what uncertainties of pipe diameter and wall thickness are considered for assessment of a 1% flow uncertainty? Oof. That's a great question. So we often like to say we often like to say that the meter is only as good as the pipe that it's on. Because when you're buying a clamp on ultrasonic, you're only buying half a meter. You're not buying the spool. So if the pipe is new and properly manufactured, then you can get very, very accurate flow. As a matter of fact, on an engineered pipe, so that means a pipe that was not only just drawn, but actually cut and polished and engineered so that we know to the tenth of a thousandth of an inch how thick it is. You can get a clamp on meter that delivers accuracy as good as a Coriolis meter at 0.1%. The challenge is that normal pipe has a great degree of difference between how thick it is or how straight it is, for example. So when you ask what degrees of uncertainty are pipe diameter and wall thickness are considered for a 1% of rate flow accuracy, I would say that standard pipe, Schedule 40 or whatever you happen to have, will most likely deliver a flow accuracy at 1% of rate or better. So standard pipe in decent condition. So that means not only is the internal condition in reasonable, you can have scaling, okay, you can have some buildup, okay, but the challenges is that the more buildup there is, the smaller the internal volume. It's very difficult for me to give you a measurement of uncertainty of pipe diameter and wall thickness for 1%, but 1% is usually the worst we do. If you want to get 1% or better, that's when you really start getting into the engineered pipe. The next question is, it sounds like it might work for steam, but this may be taking it too far. The challenge with steam is that steam is forever changing. Is it a gas? Is it a liquid? Is it a liquid in a gas? Is it wet? Is it dry? Is it superheated? The challenge is that it is so volatile in its nature that it is challenging, very, very challenging to measure steam. There are some suppliers who offer a steam system that works, I guess. I have never seen or been convinced that a steam clamp-on system is the best way to measure steam. You could use a clamp-on meter to tell you whether or not there is flow in the pipe in a gas, and a steam is a gas. But the fact that the steam is constantly changing is a challenge. I'm going to move on just a little bit here. I'll get to this next question in just a minute because again, I don't want to lose time here. All right, so built into the device when you actually set it all up and turn it all on is a startup and service wizard. So the wizards within this device step you through the initial settings and the initial setup of the device. And if you stare too long at a screen, if you're waiting too much, it'll ask you if you need help, and it'll give you a hint as far as where to go and how to get it done. So setting it up on a meter, your first meter may take an hour, your second meter may take 40 minutes, and after that it's about a half an hour, unless it's a portable, in which case it happens even faster because you save the location that you're putting it on. Another nice benefit about this device is the display. It is a true multifunction display. As you can see in the picture here, the display can show a host of data points. Flow, volume flow, sound, speed, temperature, mass flow conversion, totalizer. You can also show just one flow, one display. You can have it in big 3-inch block letters of what your flow is. Or you can actually have the display show you what the waveform looks like. And the waveform is the actual sound signal that the device has. So this becomes a critical part of troubleshooting. If there's a problem, you can actually get, yeah, here it is. You can actually get the sound wave diagnostics directly on the display. And the benefit of that is that if your transducers get knocked, or if you'll start losing signal, or perhaps you're getting a high degree of aeration because of a hole in a pipe or a leaky packing on a valve, you can use this type of tool to help identify what the problem is. This is where the micro SD card is maintained. Again, it's a up to I think it's, what did I say here? It's a 32 gig. That's right. It says right there. It comes with a 4 GB, so you can have a couple of years of memory or a couple of decades of memory. It really depends on what you want. The micro SD makes it easier to start up, allows you to write information to it. You can also access the information via USB port, which is hiding right up here that you can barely see. It's a standard USB port. It allows you to interface with a setup tool, product data manager, or PDM, product device manager, sorry. So you can actually interface directly with the device there as well. There's the USB interface. And the process device manager is a tool that's available from Siemens. You can get a device for a program for a single device for about, I don't know, what is it, 30 bucks, 40 bucks now, something like that. But it'll work with a litany of both Siemens and competitive devices. So it's a handy tool to have. So we talked about most of these. The installation is easy. What's interesting is that if you have a failure on a transducer, it takes a single person with a single new transducer or a set of transducers to fix it in a matter of minutes, instead of having to remove the entire inline flow sensor to send it back to the factory to have it serviced. The RTD used as an input doesn't need a temperature transmitter. Is the RTD directly connected? Yes. So the RTD, actually, in the very first picture, I actually showed a surface mount. I know, sorry, you're all getting epilepsy now. The RTD can be a surface mount RTD. It could also be an insertion type RTD. It could also be a thermistor. It could be 100 ohm, it could be 1,000 ohm, pretty much whatever it is you need it to be. It could be. It is what you happen to have. You could have a very involved pressure transmitter. You could take a 4 to 20 signal in. Very simple. You could take a digital signal in. It's all very straightforward. Um, so I don't need a temperature transmitter. It can just be an RTD directly input. All right. Are there any application specific questions? Where are you guys using these? Is it water and wastewater, oil and gas, chemical? Okay. Can you explain how the diagnostics work? Whoop. Yep. Can you explain how the diagnostic work using the transducer wave screen? Ah, okay. So what? Yeah, boy, I should turn my sound off now. All right. So the signal wave shapes. The wave that you're looking for usually has very specific dimensions, pretty much like what you see here. So if you see a little noise over here, or you can see dropouts out of here, or some phase differentials, you can correct for that by how it's mounted. Sometimes it could be there's too much, the transducer is mounted on the pipe, but the pipe is very rough because it's been rusty and painted for 2,500 years. So you have to really scrub down and get to the metal to get a really good signal. So the waveform can help you with the installation. Also, it can tell you if you're getting reflections, if there's other noises in the pipe, ultrasonic noises that could give you an indication of flow irregularities. So pretty much what this is often used for is troubleshooting diagnostics to make sure everything is kosher. Um, your question states, should they be synchronized? Can you explain how the diagnostic work using the transducer wave on the screen? Should they be synchronized? Um, I'm not quite sure if you could expand on your question. I'm not sure what you mean by should they be synchronized. The waveform that you're shooting for is a fairly normal distribution, kind of both above the line and below, as you can see here. You do see some synchronization between the signal, but what you would be looking for, what you would see as a problem would be a huge dropout or signal loss. I apologize if I'm not answering that question clearly. If you would like further explanation, please add. Should they be synchronized, matched on the screen? As you move the transducers around and as you alter how they're mounted and the information that is within the device, all of which can be altered. So you can actually set it so that the transducers mounted on the pipe have a single path like that, or you can move them further apart and have a multiple traverse signal so that it goes, sorry, I'm out of frame, so that the signal goes, bounces off the top, bounces off the bottom, bounces off the top. That would be two traverse. You can change all of that. And what that helps you do is to get information out of the pipe. So if you're looking at your diagnostic screen and you're seeing that you're not getting good information like this, you can set the device for a multiple traverse mount, move the transducers further away. The transmitter will tell you how far they need to be in order to get enough information for, say, a challenging gas like helium or hydrogen. There's not a lot of material there to slow the signal up. So then you would have a multiple bounces in order to get this signal through it. Again, I don't feel like I've answered that question appropriately, but I'm going to give you all my contact information in a couple of slides, and you can email me or call me directly, and we'll talk more. Pipe materials, pretty much everything that rings. Yes, plastic, PVC, fiberglass. Now, here's the interesting about concrete. Concrete can be challenging. Okay, now if it's concrete around a metal pipe, the best thing to do would be to dig through the cement to get to the metal pipe. Okay, but if it's cement, we can do it, but the cement has to be properly treated, which means cement by and large has voids in it, and the voids um, uh, impede ultrasonic signals. So you actually have to coat the pipe so material sinks into it like an epoxy in order to get the signal through the pipe so that the sound can bounce through. So yeah, we could do concrete. It's a challenge, but it can be done. Does the system have codes for diagnostic? It's got tons of them. Yes. It gives you codes, gives you faults, it logs the codes, it stores them in perpetuity. You can store them on the micro SD card for when the codes happen and when the codes are addressed. Most of them come up in relatively easy to understand English words, what they are, but some of them have codes, and those codes are, of course, all in the manuals. All right. Anything else? I did want to make sure you got this information. This is my current phone number as well as my email address. Okay. So the next question is, if the gain is dropping for the set of transducers, does it mean that the pipe parameters are changing? Change in gain very often is not a change in pipe. It means that the flow profile is being altered. The flow profile could be altered due to particulate matter in the stream, air getting in on a liquid flow, air bubbles. Usually that causes issues in gain. Gain can also be a problem in installation if you don't have a proper interface between the pipe and the transducer. All right, crude oil. we measure thousands of barrels a minute of crude oil. So yes, we can definitely do crude oil. We can do gasoline. We can do natural gas liquids, all hydrocarbon fluids. Not a problem. What is the allowed difference between the speed of sound measured by two sets of transducers? I love these questions. Um, do me a favor, email me. This is a much longer conversation than 10 minutes. There's a lot more to it. It usually it's not much. Yeah, fantastic. All right. Thank you.
Eric, thank you for your time today. Thank you for the presentation. That was great. I think we got a
My
lot of good
pleasure.
information out of it. Um, yep. If anybody needs anything else, reach out to Eric directly, and you can also contact FLW Southeast through our numerous different channels, and we'd be happy to support and help. So, thanks for attending, everyone. Thank you, Eric.
Thank you. Take care, everybody. Bye bye.
Bye.